Okay, so this is the 9th lecture, and the ring theory goes, and some of the lectures were of 2 hours and 2.5 hours. So, and the rest of the lectures were about 50 minutes, right? So, because I just wanted to finish it as soon as possible, that's why the length of the duration of the lectures are getting little bit heavy, but do not worry. So anyways, so I will start the night lecture. In the last lecture, what we did is actually we study about the homomorphisms, and we have studied also the first isomorphism theorem, and also second isomorphism theorem, and third isomorphism theorem, right? And I have also given a question in the last time, so prove or disprove one question. So what was that question? That question was uh, previous question, sorry. The question was, show that this 2 ideal generated by 2 1 plus x square is not maximal. Is not maximal. I have told you, either prove it or disprove it. Okay, so have you tried this problem? So this is ideal generated by 2 elements, right? Either 2 1 plus x square. So if you try, then it's okay, and also you have solved, then well done. And if you not solved and also tried at least, so I can give you the solution, right? So this can be proved, right? This can be proved, this cannot be disproved. So I'll prove it. Let's see what happens. So this is an ideal, right? Ideal generated by 2 into 1. Okay, this is in zx, right? In zx. So what is this? Is an ideal, right? So this is an ideal generated by 2 elements, and you want to find whether this is a maximal or not. I have also given 2 statements in the last class. I have given 2 statements. One statement I have proved, and another statement I have not proved. What is the statement? If your p is a ideal and p does not contain any p, so p does not contain any zero divisor, right? Without p is without zero divisor, if and only if r mod p is a no p is a prime ideal. P is prime ideal if and only if r mod p without zero divisor. Okay, without zero divisor, or r mod p is an integral domain. Okay, this I have proved. So what I prove is that I proved. Okay, so I will use those statements. There is one more statement. If uh, r by m is a field if and only if this is a m is a maximal ideal, right? These 2 statements I have already proved. So just a second, someone is texting me. So yeah, how do we show that? So can you see that this ideal generated by 2 is contained in ideal generated by 2 into 1 plus x square? Testing. So 2 ideal generated by 2 and 2 1 plus x square. 2 is contained in ideal generated by 2 into 1 plus x square. So so 2 1 plus x square is 2 ideal generated by 2 is contained in 2 1 plus x square. Can you see? what is the definition of 2 into pxp? So it's very clear, right? So you have to define, you have to see, you have to you have to use the theorems. What about the theorems? I have the first, second and third isomorphism theorem. In fact, first and third isomorphism theorem I'll use here. So in this structure you cannot see, it's very difficult to handle, right? Whether this is a maximal, ideal or right, you have to use the statements. So what I do is, I will define a map f from zx to somewhere, and I will make, my task is to, I should have to make this kernel of f, this is ideal generated by 2. If I can show this means this is a homomorphism. Okay, homomorphism I have to use, and I will for that I will, so that I can make zx by kernel is isomorphic to the image, whatever the image will be here. Okay, so if I can show this, so I will have what I will have, so r mod I will have r mod I, and I will have j mod I, and I will show that the isomorphic to r mod j, right? This kind of things I will show. So what is the best choice I can do such that the kernel will be ideal generated by 2? What do we think? What should I take as a codomain? What should I take? So can I take this as z to x, and I will define as a map in such a way such that the map I will define as f of as a polynomial px. What is px? Is actually summation of ai x to the power I is 1 to n. Okay, so this map I will take as, so all the so I will take this map as summation ai mod 2 s to the power I is from 1 to n. Can you see this map? And this, can you verify this map is a homomorphism plus onto this map? Suppose, see here, the map is, I have defined as a map, px is a polynomial, so ai x to the power I. So I am just applying the mod 2, because I am in z2. I have only two choices for the coefficient, right? Either 0 or 1. So I have defined this map. So what can you verify? What will be the kernel of this map? So suppose you have verified this is a homomorphism and onto. What is the kernel of this map? Kernel of this map. Can you verify this map? So let's see what will be the kernel. So all those px, that means summation of ai x to the power I is from 1 to n, such that, so f of the summation of ai x to the power I is 0 element. What is the 0 element? I is from 1 to n, 0 element is 0. What is that? This is actually all those ai x to the power I or px, such that this is actually summation of ai mod 2 x to the power I is from 1 to n. This is 0, right? Can you see? So what is this? I am only collecting all those polynomials with vanishing at which are vanishing in the as a mod 2 means. So I have, can you see, this is all those polynomial p dot 2 such that p inside zx. Can you see? px is all those polynomial px into the, so all those you have to consider all those polynomial which under mod 2, this gives you 0. Suppose that you have a1 plus, sorry, a0 plus a1 x square plus dot 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 plus an x power n. You have to choose all those polynomials such that this under modulus mod 2, it is giving you 0. So if you take this kind of polynomials p dot 2, that means you are polynomial is any types of polynomial. If you just the coefficient is modulus 2, then it will be definitely be 0. What is this? This is nothing but ideal generated by 2. So if you have this, so your kernel is this, also the map is onto, so what you can say is, you can say that as a first isomorphism theorem, zx by kernel means ideal generated by 2 is isomorphic to z2x. This is first observation that you should make. See, initially I should not have to worry about this kind of question, but I want to convince you, so that's why I have taken little bit lengthy problem or some problem which are not so easy. Okay, so that's why I have taken this problem. Okay, so first observation is this: zx by ideal generated by 2 is isomorphic to z2x, right? So what we have is, you have so your I ideal is ideal generated by 2 and j ideal is ideal generated by 2 into 1 plus x square, right? And your R is zx, right? So what you know by the third isomorphism theorem, R mod I quotiented by R mod j, j mod I is isomorphic to R mod j. Okay, so what we have is, you have R mod I. See, this is R and this is I. You have R mod I. You need to find j mod I. Need to find j mod I. J mod I means you need to find ideal generated by 2 1 plus x square in your quotient, and I is ideal generated by 2. What will be this isomorphic to something, right? It will be isomorphic to something, right? So R mod, so you need to find j mod I. So again the same process, you will find you need a kernel, right? So you need a map here like that, and you need to find, so you need a map. Suppose you need a map phi from now this is your R, that means from here to you have to define the map to 1 plus x square to somewhere, such that you have to make this kernel phi is ideal generated by 2. So what are the possible choice, so that you can make this as a kernel phi is ideal generated by 2 as a homomorphism you have to define. So what are the possible choice? So if I choose what you can choose. So if I choose the ideal generated by 1 plus x square and define the map in such a way that phi of, so here it is 2 into 1 plus x square, what kind of things it looks like? It actually look like some 2p plus 1 plus x square into q is goes to, see, we don't have to worry about this 2p. I will just send it to 1 plus x square into q. See, you are in zx, right? You are in zx, although you are in zx. Okay, this you have to you know that you are in zx. So what you have to verify, this is a homomorphism plus onto. So clearly this is onto. For any kind of this kind of polynomial, you just need the premise as this, so we don't bother about this 2p, right? So this map is going to be homomorphism also is check for the homomorphism easy, and you have to show this is onto. What is kernel phi? Just calculate the kernel phi. Kernel phi means all those 2p plus 1 plus x square into q, such that this 1 plus x square into q this is 0 because this is 0 element. What is this? This is actually 1 plus x square into p, and p inside this zx. So this has to be happened. So this implies that 2p, and this implies that q is 0. This will imply that since 1 plus x square cannot be 0, so so q should be 0. If q is 0, so I will only have 2p, such that p inside the zx. What is that? This is nothing but ideal generated by 2. So again I have what I have is this j mod I. J means j mod I, right? J means ideal generated by 2 into 1 plus x, 2 comma 1 plus x square, and 2 into 1 plus x square, right? So I, what is I? Ideal generated I is also this kernel phi, means j mod kernel phi, right? This is kernel phi is isomorphic to image. What is the image? Image is ideal generated by 1 plus x square. Can you see? So I have what I have is, I have this one r mod I also have, and also have j mod I. So I have this one. This is, you can think as r mod I, and this is j mod I. You have j mod I. So now you use the third isomorphism theorem here. So r mod I, what is my r mod I? R mod y sub r mod y, this zx by ideal generated by x, zx by ideal generated by 2. So zx ideal generated by 2. So r mod I quotiented by j mod I, means 2 1 plus x, 2 ideal generated by 2 1 plus x square by 2, ideal generated by 2 comma 1 plus x square quotiented by ideal generated by 2. This is isomorphic to r mod j. What is my r? zx. J means, so r mod I. So zx by actually r mod, see here. So this is isomorphic to r mod j, right? So this is actually 1 plus x square. Are you getting my point? This is r mod I, this is j mod I, is isomorphic to r mod j. Are you getting my point or not? Sorry, just a second, I am making a mistake. Just a second. Yeah. So what do you have? This r mod j. What is my r? R means zx. J means we have the ideal generated by 2 into 1 plus x square, because this is my j. This is isomorphic to r mod I. See here, my j is this, my j is this, my I is this, my r is this. So j mod I, r mod j is isomorphic to r mod j is isomorphic to r mod I quotiented by j mod I. So what is r mod I? R mod I means zx quotiented by ideal generated by 2, this quotiented by j mod I. J means 2 1 plus x square, this ideal quotiented by this ideal 2, ideal generated by 2, right? And this is isomorphic to this zx. So is there any zx? Not zx, actually z2x, ideal generated by 2 is z2x. This is actually z2x, and this is isomorphic to 1 plus x square. see, this element is isomorphic to this, and this is isomorphic to this. Can you see? We have just proved na. From here I am getting from here I am getting this to this, and from here I am getting that zx quotiented by ideal generated by 2 is isomorphic to z2. So what we actually we get, so zx by ideal generated by 2 1 plus x square is isomorphic to this z2x by ideal generated by 1 plus x square. See, I have made this ideal generated by two elements. I have simplified in such a way that this has been turned out to be one ideal generated by 1 plus x square quotiented by an ideal which is generated by one single element, right? So this analyzing this is really a little bit hard as compared to this, because this ideal is analyzing is far easier than this. So that's why I have, since these two structures are isomorphic, so what you can do is, so what is my question is ideal generated by 2 into 1 plus is not maximal. So what you can do is, if you can show this is whether it is a field or it has it is an integral domain, I can talk about the primality and the maximality, right? So otherwise I cannot say. So I will show, so this structure and this structure, so analyzing this structure and this structure are actually same, so is equivalent to analyzing this structure. So can you, if I can show this is not maximal, so what do we have? Maximality for that, R mod, if you have a ring with unity, so R mod M is field if and only if M is maximal. So if I can show M is not maximal, so I will show this is not a field. If it is a field, then I will show that this is a if I can show this is a maximal, so for maximal, so R mod have R mod M should have to be a field structure, otherwise you cannot. So this is maximal ideal. So I have given you the statement, also to given you the proof, right? So what is the problem here? So R mod M, so you just for maximality of M, you just see this z2x by, suppose this is your M, because this analyzing this structure and this structure is equivalent, right? So if you can show that this structure is maximal, so this structure is a field, so I will show this is maximal. So if I show this is not a field, so I will show this is not a maximal ideal, because this is an if and only condition, right? So let's see whether it is a field or not. For field, what you have to show, this every non-zero element should be a unit or it has no zero divisor, right? So let's see whether it has zero divisor or not. So let's check for this element 1 plus x square into the same element. Let's see 1 plus x and plus 1 plus x square, whether I will check that this element is, whether this element is a zero divisor or not. So what is this? This is actually by the coset operation 1 plus x square plus ideal generated by 1 plus x square, right? What is this? This is actually 1 plus x square plus 2x plus ideal generated by 1 plus x square, right? So you are in z2x, because you are analyzing only this and this are isomorphic, so you are analyzing this. If you can show this for, then you can of course show for that. So this structure I am analyzing, so in z2x this is equivalent to 0, so 1 plus x square plus ideal generated by 1 plus x square. So this element is already lying inside here, so this is actually nothing but 1 plus x square. So this element is a, so I am getting 0 element, right? So these two are a non-zero element. These two is non-zero element because 1 plus x square, 1 plus x is not in a 1 plus x square ideal generated by 1 plus x square. So this is a zero divisor, so it cannot be a field because it has a zero divisor. Okay, so this implies that this z2x by ideal generated by 1 plus x square is not a field. If it is not a field, so if it's not a field, this implies that the structure zx ideal generated by 2 into 1 plus x square is not a field, because these two structures are isomorphic na. This structure and this structure are isomorphic. See here, this and this structure are isomorphic, so this cannot be field. If this is not field, this implies that this 1 plus x square is not maximal. Are you getting my point? This is I am solving one question. So can you see that this how complicated the situation it can be? Can you see the proof now? So this proof that this 1 plus x and ideal generated by 1 plus x square is not maximal in zx. So can you see the proof now? So this is one question I am solving. Okay, so this is a little bit constructive proof here, right? So I will, since you are in a freshers, so it might be a little bit hectic, but I will give you some things. Anyways, so what I have to show is, so this is not maximal. Okay, this has been proved. So now I am giving you a general data. So what is the general data? So zx by ideal generated by any polynomial p and a function fx. No, not p, it is not polynomial. So if p is a prime, this is always isomorphic to zp x ideal generated by fx. The similar proof works here. Whatever I have proved for the 1 plus x square, the similar proof will work here. So in any ideal generated by 2 element where p is a prime and fx is a polynomial, so this zx quotiented by this ideal is always isomorphic to this zpx over zpx quotiented by this fx, right? So this is one. So this is a field. So zx quotiented by p fx is a field if and only if fx is irreducible polynomial in zp, over zp. Are you getting my point? Irreducible polynomial, I will define what is irreducible polynomial. So I'm giving you, so if degree of this polynomial f is either 2 or 3, this implies that zx quotiented by p comma f, this is a field structure. Okay, if and only if fx is irreducible over zp, if and only if fx has no root in zp. This is the meaning of irreducibility. So fx is this structure is a field if and only if fx is a polynomial. Fx is irreducible polynomial. So if degree of this polynomial either 2 or 3, this is a field structure if and only this is irreducible polynomial if and only fx has no root in zp. This kind. So mind it, this is only for the degree polynomial of degree 2 and 3. So can you solve the question if I give a question related to this theory or this whatever I have told here? So if I can give questions from here, so can you solve it? So I am giving you one question regarding this topic or this whatever I have so whenever zx quotiented by the ideal generated by two elements where p is a prime and fx is a polynomial, so of degree 2 and 3, how can you when do you say something or like that question I will ask. So so are you getting my point? If degree is polynomial 2, this structure is a field. If it is field, then you can show this is a maximal ideal, right? So if and only if it is reducible over zp, and if and only fx has no root in zp. So I am giving you one question here, you just solve it. What is the question? Ideal generated by 2 1 plus x square, maximal in zx. You have already proved ideal generated by 2 1 plus x square is maximal in zx. Ideal generated by 3 1 plus x square is maximal in zx. Ideal generated by 3 1 plus x plus x square is maximal in zx. So which of them are maximal? Which of the following is true? So which of the following is or are true? You just solve it. I am giving you 5 minutes. I am giving you 5 minutes. So solve it. Which of the, just use whatever I have used here. Whenever this is a field or maximal ideal, you just solve it. Just a second. So which of the maximal ideal, you have to check for the maximality. Solve it. Automatically Wi-Fi getting off. Don't know why. Okay, so time is going to up. So okay, this is, I don't think this question should have to take, you should have to take 5 minutes. So anyways, I'm okay, still it is getting, stop it, I should stop it, because this question does not make any sense for 5 minutes. Anyways, so what you can do is, I don't know, this board is really okay. So what is so this is not maximal, we have proved, so there is no, so this is not maximal, already proved. Okay. What about this question number no, the option, what about the option is 2, or suppose, yeah, what about the option 2? So what I have told you, this is a polynomial of degree 2, right? So if it is polynomial of degree 2, this is maximal, so you have to show this is a field. If this is a field, then this ideal will, then this ideal will be maximal. All you need to check, just need to check is this is a field, whether this is field. So this is a field if and only if fx has a root in ZP. So for 2, what you have is, you have to check 2 1 plus x square. So this is my f and this is my p. So you have to check in Z2 this polynomial has root or not. Does it have any root? Suppose f of 0 is 1. F of, what will be f of 1? F of 1 will be 2, and f of 2 will be 2 to 4, 4 to 6, 6 7. what will be 2? 7 means, that means you need 0, right? You need 0 in Z2 over Z2, right? You are finding this over Z, no, sorry, this is not, f of 0 is 1, because 0 0 1. What will be f of 1? F of 1 means 1 1 2 3. 3 means, what is 3 means in Z2? 3 means 1. So f of 0, so this implies that this has no root in Z2. Z2 means 0, Z2 means 0 and 1 na? It has no root in Z2. So this implies that if it has no root in Z2, so this means that this is a field. This means that this ZX ideal generated by 2 1 plus x square is field. This implies that ideal generated by 2 1 plus x square is maximal. What about the question number 3? 3 1 plus x square. 3 1 plus x square, ideal generated by 3 1 plus x square. What can you say whether this is, so in Z3, right? I have to check in Z3. So what is f of 0? F of 0 is 1. What is f of 2? Sorry, f of 1. F of 1 is 2. 2 means 2. And what is f of 2? F of 2 means 2 to 4 5. 5 means 1. Oh sorry, 5 means 2 in Z3 na. 5 means 2. So this implies that no root. This implies that maximal ideal. So what about the question number 4? 3 has been done. 4. Question number 4. What will be the question number 4 is actually give us 3 1 plus x plus x square. You have to check this. So you have to check in Z3 whether this polynomial has a root or not. So let's check. So you have to check whether this polynomial has a root or. So what is f of 0? This implies that f of 0 is 1. So what is f of 1? 1 1 1. So this is 0 because this 1 is a root. So this implies this 1 is a root of f in Z3. This implies that this ideal 3 1 plus x square is not maximal. Because this is not a field ideal generated by. So if and only condition, now you have to be careful for that. Okay, so this question has been over. So now I am going to start Boolean ring because I have spent so many times here. I'll have to I think that I was supposed to solve one more question, but no, I will not solve this question. I will solve this in the last of the lecture or in the question solving session. So now just I will define Boolean ring. What is Boolean ring? Boolean ring. What is Boolean ring? Boolean ring, you know, this r plus dot is a Boolean ring. Boolean ring if x square equals to x for every x inside R. Every element is of the type x square equals to x. That means you take any element and you just multiply it again, that is with respect to the second operation, you should get the same element. That means every element is an idempotent element. Okay, so so what are the properties? I'm writing the properties. So x square equals to x, what does it mean? X into x minus 1, this is equals to 0. This implies that x is either 0 or 1 or 0 divisor. Can you see? This implies that in a Boolean ring, so in a Boolean ring, every element is either 0 or 1 or 0 divisor. Why? This because of this statement. Okay, what is the second? This is 1, this is 2. So if a Boolean ring contains more than one element, so it either 0 or 1 or a 0 divisor, right? So if it contains more than one element, more than two elements, so it must contain a 0 divisor. Are you getting my point? If it contains more than one element, suppose this cannot have two one element, right? So it must have 0 and 1. Okay, 0 and 1 will be by default, and if it contains more than one element, so it must be a 0 divisor because it cannot be repeatedly 0 and repeatedly 1, right? So I am writing a Boolean ring with more than two element is never an integral domain, hence never a field. Are you getting? Because if it contains a 0 divisor, so it cannot be an integral domain. What is the definition of integral domain? It does not have any 0 divisor. So if it contains more than two elements, so it will not remain an integral domain. It will contain at least one 0 divisor. So if it contains at least one 0 divisor, it cannot be an integral domain. So if it cannot be an integral domain, it cannot be a field, right? Now I think I'm clear with the Okay, so if a Boolean ring, this is third, a Boolean ring R is a field if and only if R is isomorphic to Z2. There is no other choice. What can you think about the characteristic of the Boolean ring? Let R be a Boolean ring. Boolean ring. Then what about the characteristic of? So if it is zero ring, then 1. If R is zero ring. So what if it is non-zero ring? So what it should satisfy? X square should be equals to x. This property should satisfy, right? So you can write that a plus a that square equals to a plus a. You can write it. So this means that a square plus 2a. This implies that a plus a. This implies that a means a square, a plus a. This is equal plus 2a. This is equals to a plus a. This implies that 2a equals to 0. 2a means 0 means for every 2a is 0. That means the characteristic of this for every a, okay, that is for every a inside the ring R Boolean ring. So this implies the characteristic of 2 if R is, so otherwise characteristic of ring, otherwise characteristic of Boolean ring is either 0 or 2, no sorry, either 1 or 2. If it is 0 ring, it is 1, otherwise 0. What is the fifth property you can point out? So what do you think about Boolean ring is commutative? Is Boolean ring is commutative? So suppose that what is a plus b third square? This is actually a plus b into a plus b, and this is actually a plus b because of the Boolean ring. So this implies that, so this is a square plus it will be b square plus ab plus ba is equals to a plus b. So a square equals to a, right? A plus b square equals to b plus ab plus ba equals to a plus b. This is implies that ab plus ba, this is equals to 0. This implies that ab equals to minus ba. So if it is minus ba, so you can write it as ba because the characteristic of this ring is either 2 or 1. 2 or 1. So you can write minus b as b. They are same, but that means you are in Z2. Suppose you are in Z2. So characteristic of the ring is 2. So minus b and b are same. So ab equals to ba. This implies that ab equals to ba. This implies that commutative. So Boolean ring is always commutative. Ring is always commutative. Commutative. So that's, you just assume it. Okay. So what the last and important but not the least property. So this is an important property in a Boolean ring. I will prove it also. In a Boolean ring with unity, you need the unity, right? An ideal is maximal. An ideal I is maximal if and only if I is prime. So it's very, I'll prove one here. So proof. How do you prove? So suppose something is maximal or something is prime, we just use those two statements whichever I have defined in the last class. So I have to check whether this is maximal or prime. So suppose the reverse part I will do. Suppose P is PBA. So I is here, right? So I is prime ideal. You have to show I is maximal. So for I is maximal, I will show that my claim R mod I is a field. if I can show the R mod I is a field, this will imply if and only if, as a this is in fact as if and only if condition. So R mod I is a field if and only if I is maximal, right? So that's not a matter. So R mod I is a field. I will show that R mod I is a field. Suppose that let x plus I is an element of R mod I, and x is in R but x is not in I, because if x is in I, then this will be definite I, this will be nothing but I. So x is not in here, right? So x is not in I. You have to be conscious about that. So x plus I is a member of R mod I, right? What can you think about the x plus I into x plus I? This is x square plus I, and x square equals to x plus I. So this is two cosets are same if and only if x square minus x is inside I. Are you getting? This means that x into x minus 1 inside I. What does it mean? I have assumed that I is a prime ideal. I is a prime ideal. This will definitely imply that either this implies that x inside I or x minus 1 inside I. So x cannot be inside I because I have assumed that x is not inside I. X cannot be inside I. This will imply that, so x is inside I. So this implies that x minus 1 is here. X minus 1 inside I. This implies that x is inside 1 plus I. So all the cosets are of the form 1 plus I. Are you getting? So I have assumed that x is in R but x is not in I. Okay. So I am getting that all the x plus if I can take x plus I inside from R mod I, so this will be definitely look like some x plus x will be some 1 plus I. So 1 plus, so I have assumed that x inside x plus I inside R mod I, x plus I inside R mod I have assumed, right? And x inside 1 plus I, so x inside 1 plus I. So this will definitely make sense that your cosets are nothing but there is two distinct cosets you have. So R mod I will contain, so every x, whatever x you take here, x plus I, this will be of the form 1 plus I. There is no other choice. Every x plus I you can take from R mod I. R mod I is a collection of cosets, right? So R mod I is nothing but this 1 plus I. Whatever you take x plus I, whatever you take 1 plus I, this will be some 1 plus I. Whatever you take, so it will be some 1 plus I. So what are the elements? R mod I will contain, so you have I must be there, and 1 plus I. There is no other element, and this is isomorphic to Z2, and Z2 is a field. So this is a field. This implies that if and only if I is maximal. The last lecture, if you have seen the last lecture, then there should not have any problem. If you have not taken the last class, there will be a problem, because I am continuously using the statement from the last class, statements whatever I have proved in the last class. Okay, so this implies that I is a maximal ideal, right? So this proves the statements. So this is maximal if and only if I is a prime ideal. So should I solve some questions, or should I have to focus on concepts? So let's yeah, I will solve the question. So yeah, let's solve a question. This is easy question, that's not so hard. So question: R is a ring, all those functions from 1 to 10 to Z2. There is no continuity, nothing is here. Just I have to collecting all the function from 1 to up to 10 to the set Z2, the set of all functions. So then option R has a unique maximal ideal. Option B, every prime ideal is maximal in R. Option C, every element of R is idempotent. And the last one, none of the above. This is an easy question, just think for 1 minute, then I will solve it. So try to link with the Boolean ring, whether this ring is Boolean ring, then clearly one statement will be true. So see, let's see whether this ring is a Boolean ring or not. Let f be an element of this ring. So let's see what is f square. So f square means f dot f. This implies that, okay, so let's do it formally. F square x, what is f square x? This is fx into fx. So this fx will lie into z2, right? This fx will lie into z2. This implies that f of x square, this is also an element in z2. So in z2 every element is idempotent or not. What do you think? Fx square, z2 has 0 and 1. So 0 square is 0, 1 square is 1. That means 1 plus 1 square is 1. It's not it. So this implies that this fx square equals to fx, because this is in z2. So this will definitely imply that this f square equals to f for every element f inside the ring R. Are you getting my point? In the you are in a Boolean ring, so 0 square equals to 0, 1 square equals to 1. There is no plus operation, there is dot operation, right? So this is fx. So this implies that R is Boolean. If it is Boolean, so one statement is, so every prime ideal is maximal. Every prime ideal is maximal. So this statement is true. What about first and third? Every element of R is an idempotent element of R. This is also true, because f square equals to f for every element f. So this is also true. What can you think about the statement R has the unique maximal ideal? Does R has the unique maximal ideal? So can you construct an ideal which is both are maximal? So what do you think this ideal z2 cross z2, rest all are z2. This is a maximal ideal, right? Because you cannot dominate this inside some ring, inside a proper ideal of this z2 cross z2 cross z2, whatever. This is a maximal ideal, right, in here. So what do you think about this z2 cross 0 cross z2 cross dot dot dot, how many z2s are there? This is also maximal ideal. So this and these two ideals are not same. So this it does not mean that R has the unique maximal ideal. See here, the set of all functions from here to here. It's not it. I'm collecting all the functions from here to here. So I am collecting all those z2s. These are max ideals, right? So actually our ring is this R is isomorphic to z2 cross dot 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 cross z2. It's not it. It is 10 times, because there is 10 elements here. So every element has two choices, either one. So 1 has two choice, 2 has two choice, so whatever. So this R is isomorphic to this z2 cross z2 cross z2, so whatever you can define the map here. So this is not maximal. So similarly z2 cross 0 cross z2 cross dot 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 10 times z2 is also a maximal ideal. So these maximal ideals are not unique. So this statement is false and this is also false. So these two statements are true. This is a quite easy question. So I'm not, and should I have to do some more questions or should I have to end the lecture? So let me see what I have left out with. Okay. So okay, let me finish with some something, some of the things. So let's discuss about some matrix ring. Okay, so let R be a ring. Let R be a ring. What do you think about this M and R? What is M and R? This is actually, so all those matrix A is of the form Aij of n cross n matrix, so that the entries are from this ring R. These entries are from. So if, what do you think about if R is commutative? If R is commutative, does this imply that Mn of R is commutative? This is a very easy question. So it does not imply, right? Because R is commutative means the entire here, the quantities here, these elements are commutative, these elements are commutative, but it does not mean that two matrix should have the commutative, because M and R, suppose if you take this R to be the as usual real number, so M and R is not a commutative ring, right? So that is definitely does not imply such a thing, right? So it does not imply that this M and R is commutative, right? So what do you think about if R is with unity 1, does this imply that M and R is with unities 1 1 1 1 0 0? Does this imply that? Suppose that it has the unity 1, so only you can show that this is, and this is also if and only condition, not like, so if you have this R with unity 1, so M and R must have to be unity 1 0 0 0, because this is very easy to prove. So this is an if and only if condition, right? So what do you think about the third statement? If I is an ideal of R, does this imply that Mn of I of an ideal of M and R? Think. What do you think about that? Yeah, it is true. Mn of I is an ideal of Mn of R. So why? You should have to prove in yourself homework. It will imply. And what else is? And in fact, you will show that all the ideals of M and R are of the form of the form Mn of I, where I is an ideal of R. All the ideals of Mn are of the form Mni, where I is an ideal of R. What do you think about that? Yeah, this is true. But how do we show that? So I'm giving you a little hint here. So suppose my R is R, and I am talking about this Mn of R. R means the real number R, and I is an ideal of R. And the field, this field has two ideal, right? Every field has two ideal. Either this is 0 or this is entire R. So this I either 0 or the entire R. There is no other choice. If it is 0, because this field has, I have already proved that this field has only two ideal. Field can have at most two ideal. So field has by default two ideal. That means there is no proper ideal here. So in field every non-zero element is finite. So if it contains a unit, so I will be the entire ring R, right? So anyway, so if I is 0, so this implies that this Mn of 0 is a maximal ideal in Mn of R. But Mn of 0 is not a prime ideal in Mn of 0. Why? In Mn of 0, okay, not Mn of R. So since 1 0 0 0 and 0 0 1 0, this is not inside Mn of 0, this is also not inside Mn of 0, but this 0 0 0 0 is inside Mn of 0. So this implies that, this statement implies that not a prime ideal. I am writing one statement here. In a C array, in a commutative being with unity, every max ideal is prime. But not conversely. Why? Conversely, why? Because 0 is an ideal in Z, and this ideal generated by X is a subset of, is contained in ZX. So every in a commutative being with it, every maximal ideal is a prime ideal. Okay. If every maximal ideal is prime ideal, so generally maximal ideal does not imply that it is a prime ideal. Okay. So now I am going to do some works here. Okay, let's do some works here. So, and I'm asking a question, what do you think about the ZX by 5ZX, quotiented by 5ZX, and this Z5? Are they isomorphic or something? What do you expect from them? Are they isomorphic? Let's see. Suppose you have a map F from Zx to Z5 of x. So can you define if it in as something like this summation of ai xi, I is from 1 to n, to summation of ai mod of 5 x ki power I is from 1 to n, and this is a homomorphism. You can write onto ring homomorphism, onto ring homo. What will be the kernel of f? You can verify this. Kernel of f is equals to 5zx. If it is 5zx, so zx quotiented by this 5zx is isomorphic to z5. Sorry, yeah. So in general, zx, it's disturbing, zx quotiented by mzx is isomorphic to zm of x, and this is further isomorphic to z by mz x. So this should have to write clearly zx. This is actually zx. Oh, this is actually zx quotiented by mzx is isomorphic to zm of x, and zm is isomorphic to mz by mz. So that's easy. That's easy. So if I is a maximal ideal, asking one question: if I is a maximal ideal, I is in R, does this imply that this Ix is maximal in Rx? In Rx, what do you think? Is it true? So let's whenever this kind of statement asks, so you just think about the very basic thing. So let's take R to be this, R to be Z, and ideal you take this will be ideal generated by 5. This means this is 5z. This 5z is maximal in Z. Is not it, because this is a prime number, and 5z you cannot enter 5z, you cannot dominate into a proper ideal of Z. Okay, so this 5z is maximal ideal, right? So let's take this Ix to be 5zx. So 5zx. So what do you think about this zx quotiented by this 5zx? This is isomorphic to z5 of x, and z5 of x, this is not a field, right? Verify that this is not a field. What do you need to check for the field? Every non-zero element should be an unit. Okay, so this is either, if you can show this is not an integral domain, this will be also enough. If it is, this implies that this 5zx, if it is not a field, you have to verify this is not a field. So this 5zx is not maximal in Z. So here 5 is a maximal ideal in Z, but this 5zx is not maximal in the ideal in Zx. Okay, in Zx 5zx is not a maximal ideal in Zx. So that's the idea. So this does not imply. And last thing, I will end this lecture as by defining this. Suppose I is an ideal of the ring R. Define a map F from Rx to R mod I x. And how do you define this f? Summation ai x key power I is from 1 to n. This is actually summation ai plus I. The similar, actually this is actually modulus I is from, sorry, this is not from 1, this is from 0. I is from 0 to n x key power I. This is a onto ring homomorphism. What is the kernel of f? Kernel of f will be this of ix. You just verify it. And so what you will do is this rx by this ix is isomorphic to r mod I. This is a very nice thing. This kind of thing we need whenever we will solve this question. So rx quotiented by ix is isomorphic to r mod I x. Okay. So rx quotiented by ix is isomorphic to this. Okay. And yeah, that's all, I guess. And should I define correspondence theorem? Correspondence theorem, what it says, suppose n is a ideal in R, so then there exists 1-to-1 correspondence between ideals set of ideals of R containing n and the set of ideals of R is R by R mod n, and the set of R mod n. This I am giving you as a homework. This I am giving you as a homework. You just prove it. This is called correspondence theorem. This is also in also have in group theory course. So n is a ideal, and in the group theory course we do have the normal subgroup. So there is a 1-1 correspondence between the ideals of R and the R containing n and the set of ideals of R by n. That is a 1-1 correspondence. That's it. So this lecture is up to that, and this that's for today. We'll meet in the next lecture. Okay, thanks for watching.